All right. Welcome, everyone. I do, in fact, have the homeworks graded. I haven't gotten around to posting the grades on Canvas, but they are graded, so you can collect your homework 5s for those who are here today. And I've recorded the grades on my computer in my office, right? So, I have your grades written down. I just, again, haven't uploaded them to Canvas. For those who submit their homeworks online, I have those graded as well. And again, I'll post the scores after class today. But yeah. Otherwise, I posted that survey, right, about the exam day. I have not looked at all as to what current responses are. I even forget when I made the survey due by, but yeah, I'll send out an announcement based off of kind of those results whenever it is due, or past whatever the due date is. I assume I did probably this Friday. I don't know. You had some nods. Yes. Okay. Yeah. So after this Friday, I'll send out an announcement on Canvas about if anything's changing related with the third exam date and things like that. Okay. I guess I'll just make a note that, right, I've had a couple of people talk to me about this already in this class or my Gen Chem class, right? But all right, we have right after Thanksgiving break, we have a week class and then finals, right? And so if there's anyone that feels like they would rather just not come back to campus for those two things, right? We're basically taking the 2 exams, and doing like the review and such in person. Like, you're welcome to take the exams over Zoom, attend the review via Zoom, things like that, if that's what you prefer. Right, I think homework 6 is due on Monday next week, right? So it's due before the break, right? Yeah. So, but I mean, even if you wanted to turn in homework 6 virtually, you could as well, right? But so if anyone is feeling like doing that, feeling like, you know what, I don't want to come back to campus after going home or whatever, for whatever reason, whether it be kind of related with, concerns over coronavirus or crap like that and traveling, or if you just don't feel like coming back, you know what I mean? I don't really care what the reason is, but you're welcome to do so. I'm not gonna force us to go virtual. I know there's some classes, some faculty members that I have just made the decision to just do that last little bit virtually. I'm gonna be around. I'm not going anywhere for Thanksgiving, things like that. I got no one coming in town and blah blah blah. So I'm going to be here, be around. So I'll offer face-to-face instructions and things like that for anyone who still wants it. And and taking the exams in class and things of that nature. But if you want to not do things in person for that last week of class and the final, that's fine with me. Just make sure to let me know so I can add you to the list of people who get access to the online stuff. Okay. So yeah, I think that's kind of it for general announcements. Are there any questions for me before we get going here? All of a sudden remembered that at some point, usually they do like student evaluations of faculty, right? I wonder how that's going to work this semester. They're even doing it or what? I don't know. Over? Oh, you guys got? Okay. And told. I don't know. Yeah, I don't know. So, but I mean, I doubt we're doing it in person because of the fact that most classes aren't in person, or they're like this class and hybrid and yada yada. So, but yeah. So yeah, any comments, questions, concerns?
I was overall great on the homework.
Fine. Well, most of the homeworks are okay. I don't know if that's people work on them together and things like that. So that's why kind of the average score in the homeworks not really reflective of the exams. If people feel the homework questions are not as difficult as the exam questions, or kind of what that is. But typically the homework average is not, not bad at all. Like the scores that are posted on Canvas and are written on your things are without any kind of good faith points added to them and things like that, right? So those averages are even without good faith points are more than fine. So, I mean, I guess I don't know if anyone wants to voice their thoughts on it or whatever, but any of you who are taking the homeworks and taking the exams have thoughts on as to why the homework is not reflective of the exams? Is it because people working together using outside resources having more time, or is it question difficulty levels? Time. Okay.
Outside resources.
Time.
6 hours on homework versus and I
Yeah.
have my notes, so I get to check all my equations.
I see. Okay. Yeah. Okay. Fair enough. Yeah. So, yeah, that's something that because I instituted doing this homework and making it required. When I first started teaching the course, the homework wasn't required, and I started making the homework required because I felt like it's good to do it to get that practice. And scores did go up between before and after making homework required. But but it's still, a question of with exam scores are still not reflective of homework scores. And again, whether that is just kind of a time thing and notes and other things like that versus difficulty levels. I try not to make the exam necessarily more difficult than homework or things like that. Yeah, the homework questions are more difficult than the exam. Some of them, yeah. Okay. Yeah. Okay, but it's just kind of time and things like that. All right. Yeah. The other issue though with the exam is like if I try doing fewer questions, right? But then more time per question is if you don't happen to know like the one of two questions that's asked, then you're basically screwed on the exam, right? Like so it's kind of a give and take, right? Like you only ask like one question on the exam and you get plenty of time to do it. If you do not know how to do that one question, if you didn't happen to study that one thing, then you're kind of screwed, right? So it's it's interesting thing, but trying to try to get better making the exams. But yeah, okay. So, any other comments, questions, thoughts, concerns? All right. So again, right. We'll talk today about Boltzmann statistics. Okay. Today we'll have a little bit more stuff to go over than we did on Monday for sure. Okay. So the idea behind the Boltzmann distribution, Boltzmann statistics, just starts off with the idea that we have a set of discrete energy levels with a bunch of molecules in a container that can occupy these different energies, right? So I have n total molecules that can potentially be in any of these energy levels, epsilon 1, epsilon 2, 3, right? The energy levels don't have to necessarily be equally spaced as shown on the diagram on the right, but that does change things. But in terms of the Boltzmann distribution, Boltzmann statistics, there's no assumption as to the relationship. What are the differences between epsilon 1 and 2, 2 and 3, 3 and 4, and things like that, what that gap is, right? So it doesn't have to look like the energy diagram on the right of the slide here, okay, in terms of equal spacing and such, but you know, but that's just kind of an example of what we're talking about, okay? And why we consider all of this is because, as we'll find out next semester in quantum mechanics, this is kind of what energy looks like on the quantum realm, is discrete and not a continuous quantity. So, so this isn't just make-believe and fantasy, unless you consider quantum mechanics make-believe and fantasy, then sure. Okay, but yeah, so we were going to consider a bunch of molecules in, say, a container that can all occupy different energy levels, and multiple molecules can be in a given energy level, right? They don't all have to be separated in different energy levels. You can have multiple molecules within a level, right? And so within these molecules being in these energy levels, I can then talk about kind of the configuration of molecules, right, within that energy, right, where I can have some given configuration where I have N1 molecules in energy level 1 and 2 molecules in energy level 2, so on and so forth, right? So that I can kind of use this notation, right, where this is like energy level 1, then energy level 2, then 3, then 4, then 5, right? And so on and so forth, right? Where I can have a distribution of molecules in these different energy levels, okay? Right? Okay. Right, and that is going to be a given configuration, okay? Right? We're going to assume that there isn't any interactions between these molecules, right? So the energy that a molecule has is just related with the energy level it is in, okay? So the total energy, okay, is just the sum of the energies of all your atoms, right, or molecules, which is going to be related with the number of molecules in the ith level times the energy of the ith level, right? So if I have 5 molecules in the ground state, the lowest energy here, 3 molecules in the state above it, right, my total energy would be 3 epsilon, because I'd get 5 times 0 plus 3 times epsilon, right, and so on and so forth, right? So that's what that formula is saying, right, is that the total energy is the sum of the energy of all the particles that you have, okay? And that sum can be written in terms of this notation we used in the previous slide of n sub I, meaning the number of molecules in the ith energy level times that energy, epsilon sub I, okay? And then we're also going to assume for this Boltzmann distribution, Boltzmann statistics, that there's no reason a molecule prefers one energy level over the other, okay? Again, not thinking about like, you know, what is your available total energy or crap like that, but just more, right, that there's nothing drawing, no extra interaction drawing molecules into one level over the other, right? They're equally weighted, right? If this was instead of different energies, but just say different locations in a room, right? There's no location in the room that is more favorable for the molecules to be in than the other, right? So if instead of imagining you're distributing these particles over energy, you're instead distributing the particles over a container, right? That it's just saying, right, the particles equally distribute over that container, right? There's no favorable place in the container they want to be, okay? Right? And the importance of that is just to then be able to say that the chance of being in a certain energy level, a certain spot in your container, right, is just given by, combinatorics, right? Just kind of statistics that we talked about last time, right? Right, dealing with the number of ways you can put particles in those containers, right, versus the number of different ways you can put particles anywhere, right? And so, like, the weight of any given configuration, okay, so W here, I'm calling the weight, right, is, right, So the number of ways you can place your particles in those n particles in this container, right, is going to be given by n factorial, right? Because the first particle, right, yeah, right. I have one plate, like if I had one particle, I have that one particle can be placed in any of those bins, right? And I got one, or I got n ways I can arrange that particle. How am I trying to explain this here? How this comes out to be n factorial over this stuff here. Right. I mean, I guess the one thing I'm trying to emphasize here is this W, this weight, isn't what we talked about last time with probability of being in a certain, having, say, multiple heads and a coin flip or whatever. Okay. Because this is a number that's much greater than 1. This is the weight. This is instead of, this is sort of like you could imagine kind of the numerator in that probability, right? Where the total number of different ways I can have two heads over the total number of different outcomes, right? So this weight is sort of the total number of different ways I can have N1 particles in bin 1, N2 particles in bin 2, N3 particles in bin 3, so on and so forth, okay? So that's what that weight is saying. It's saying, you know, what is the weight of having this type of configuration, right? The N1, like the number of particles in bin 1, number of particles in bin 2, number of particles in bin 3, right? How many different ways can I arrange those particles to have those number of particles in those specific bins, right? Okay. That's what that weight is. Okay? Does that make sense? What weight is referring to? W, right, is again, how many different ways can I put two particles here, two particles here, two particles here, three particles here, one particle here, right? How many different ways can I rearrange those particles to have the same occupation within those bins, right? But different particles in different bins, right? And so that's what this weight is referring to, okay? Right? And again, this then goes off that assumption that there's nothing favoring any of those bins, right? So it's just a pure kind of combinatorics problem. It's a pure problem of counting, right? Let's just count the possible ways I can arrange my particles in this specific order, right? Okay, and that, you know, each different configuration has then a different potential occupation of particles in these bins, right? I could have something where I remove 5 particles from bin 1, add them to bin 2, add 2 of them to bin 2, and add 3 of them to bin 3, right? And that's a different configuration. That's going to have a different weight to it, right? Right. And if you were to plot like these weights versus kind of bin occupation, right? You would have the largest weight with the particles occupying all bins equally, right? And the lowest weights would be having the particles kind of localized in one bin, right? Okay, right. So this weight parameter, this weight here is just basically, right, kind of saying, you know, would want all particles to be separated across all bins, right? Now there's a constraint in our problem, okay, right? The fact that one, I need to, if I have some total energy, I got to conserve that energy, right? That I can't just put all particles in whatever bins I feel like, right? If my system has some total energy, right? Then I got to make sure that this configuration of particles in these bins satisfies my total energy, right? You know, so if I were to do something like this, right, right, I would need to make sure that this new configuration has the same energy as my old configuration, right? Which might not be the case because you're moving particles from the lowest energy and putting them in the higher energies, right? It'd be more, if you removed some from bin 3, added a bunch to bin 2, and maybe a couple to bin 5, right, or something like that, right, or bin 1. Okay, but right. But again, so we have kind of this weight, which describes the number of ways we can occupy particles in these bins, okay? And again, we're interested in what is the probability that we'll have a particle in a given energy level, right, given kind of the constraints of the fact that the total number of particles is conserved, right, and the total energy is conserved, right? But again, I want to look at, right, what's my probability of being in a certain container, which is related, okay, with this weight, right? Because the probability of having a certain configuration, right, having a certain configuration, N1, N2, N3, so on and so forth, right, probability of having that configuration is just related with this weight, okay, the number of ways that I can orient my particles in that configuration divided by the total ways I can move my particles in this container, right? Well, the total ways I can move my particles in the container is independent of the given configuration, right? It's the same, right? If we were doing that coin flip problem, right? If I wanted to know, right, what's the probability of getting 1 heads out of 4 coin flips, right? The total number of different coin flips is still 2 to the 4th. It's still 16, right? So the denominator is unchanging no matter what I care about for my numerator, okay? And so if we want to kind of talk about what is the optimal, the most likely probability, right? What weight is the what occupation, what configuration has the largest weight? Okay, to solve that, I can just solve taking the derivative of the weight with respect to given occupations within an energy level. Okay, now here you use the logarithm of the weight instead of the weight itself, just because it simplifies some of the math, because this weight deals with these factorials and products of factorials and things like that. Okay, but the maximum of a function is still going to be the same place as the maximum of the logarithm of that function. Okay, the maximum value is different. What the heck did I just do? What? Okay. Right, the maximum value will be different, but the location of the maximum, right? Its location on the x-axis is the same, right? Whether you're plotting the function or the logarithm of that function, right? Or the natural log, right? The location of maximums is unchanged by taking the natural log of your function, but the value is different. Okay, but this just makes the math a little bit easier to use the natural log of that weight. Okay, and so again, what we're interested in is what occupations of the different energy levels gives me, right? What combination of occupations of the different energy levels gives me my most likely occupation, right? Right, but again, we need to consider that with the constraint that I have a constant total number of particles, right? If I move 2 particles from energy level 1, I got to put those 2 particles in some other energy level, and that I need to conserve my energy, right? That the sum of the particles times their energies still has to equal some total value. Yeah.
So, and not like when you're solving for 0, like that's on the maximum weight, the maximum distribution, the distribution that gives the largest weight.
Yeah.
Okay.
Yeah, that's what we're trying to find is the maximum of this function, right? What distribution gives us the largest weight? That's going to be the most likely distribution. And so if you were to take this derivative, okay, and solve for occupation n sub I, okay, the book does it in detail. People are curious, I can go over it in detail, doing that derivative and things like that. These factorials, it uses some assumptions that the natural log of n factorial for a very large value of n is, what is it? Is it just like n squared minus n? Or I forget what it is. I don't remember off the top of my head. But there's an assumption you can use for the natural log of factorial when that factorial is a very big number to basically get rid of the factorial so that you can actually take the derivative. Because I don't want to take the derivative of n factorial. I'd rather take a derivative of like n or something like that, right? So you can kind of do that, but then you have to do this optimization with some constraints. So you have to do a constrained optimization, the method of Lagrange multipliers, if anyone's ever heard of that. there's some different mathematical techniques you got to use to kind of solve this problem. Okay, and when you do that, you get that n. So you would solve for n sub I, which gives what is the maximum, what is the optimal n sub I, and that will be related with this function here multiplied by like n total. So it's just dividing by n. Okay, and so you get n sub I divided by n, which is the probability of being in the ith energy level, is related with this function here, e to the minus beta epsilon I, divided by sum of j e to the minus beta epsilon j. Okay, that denominator we call q, which is again just the sum of the e to the minus beta epsilon I over I, right? It's called q, and this is the Boltzmann distribution. Okay, this gives you the probability of being at any given energy level in your system, given these energies epsilon I, and then this beta value we'll talk about in a second what it is. Okay? But again, this distribution, right, is derived just assuming you have discrete energies, you are conserving your energy, right? You're conserving your number of particles, okay, and that there's no interactions between molecules within a bin or between bins or things like that. Okay, and you get this distribution, right? So, so while it seems like we've added some kind of assumptions and things like that to it, right? In general, this is a very general expression that can be applied to a wide variety of problems. Okay, when we talk about molecules having, occupying certain energy levels and things like that, having certain vibrational energies or rotational energies or translational energies or blah, 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 right? So Boltzmann statistics can be applied to a wide range of things, right? Boltzmann statistics is where you get the velocity distribution of particles, right? Of particles in the gas phase, right? The velocity distribution function is obtained from this probability distribution, okay? It's using the energy is the kinetic energy, so it's related with 1/2 mv squared and things like that. And you got to kind of normalize your probability distribution, things like that, and that gives you that velocity distribution, which then gives you, right, which then allows you to calculate what is the average velocity, the root mean square velocity, and blah 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 for gas phase particles. Okay, all comes from this Boltzmann distribution. Okay, right, amongst many other things. Okay, so this is a very used distribution. Yeah.
In the partition function, why do we go from I to J?
So I use a J here to indicate that this is not summing up the numerator as well. The sum is something independent, but this is an arbitrary index. So I could call this J, I could call it X, I could call it Q, I could call it, a dog or something like that, right? Like it's just some arbitrary symbol, right? I, J, L, E. Yeah. I just called it J down here to make sure that you aren't, that we don't think that the sum is summing the numerator and the denominator, right? This is just a sum within the denominator, of this stuff here. So, other questions about this distribution function? If you want to see the derivation of this, I can do it after class, or just look in your book. It's there. Okay, just literally doing some derivatives and things like that. But yeah, okay. That beta, this beta here, you can also work out given your constraints. The fact that beta ends up being equal to 1 divided by kT, where K is your Boltzmann's constant. Okay, T is your temperature, right? And so this Boltzmann distribution here is e to the minus epsilon I divided by kT divided by Q, the partition function, which is the sum over I of e to the minus epsilon I divided by kT, right? So wherever you see beta, that just equals 1 over kT, okay? And then often, especially in next semester in quantum mechanics, we'll talk about the relative populations of certain states. And for that, you just take probability of I divided by probability of J, which is related with n sub I divided by n sub j, right? Going back, right? The probability of being in energy level I divided by the probability of being in energy level j is n sub I divided by n sub j divided by n, right? So the n's cancel and you're just left with n sub I divided by n sub j. And when you plug that in, the partition function goes away, and it's just e to the minus beta epsilon I divided by e to the minus beta epsilon j, which is e to the minus epsilon I minus epsilon j divided by kt, right? Energy difference divided by kt, okay? And also note that this functional form for the Boltzmann distribution function might look familiar to your Arrhenius rate constant expression for temperature, right? The Arrhenius rate constant expression for temperature is the Arrhenius kind of prefactor A times exponential of minus activation energy over KT, okay? That is basically coming from this, that like n sub I is your transition state, n sub j is your reactant, right? And that the probability of getting up and over that transition state is related with the probability of your particles having energy for that transition state energy, okay? Which is going to be then epsilon I minus epsilon j would be that transition state energy, okay? So that Arrhenius rate constant expression you can derive from Boltzmann statistics, you know, using transition state theory and such, you can derive that, okay? So again, these Boltzmann statistics come up all over the place, okay? Right? Even if you haven't directly been told as to where they come from, a lot of the things that we've seen in chemistry are use this Boltzmann statistics behind the scenes. Okay? Right. So again, this is the Boltzmann distribution, right? That Q is the partition function. It's very important for statistical thermodynamics with relating macroscopic quantities to microscopic quantities like your internal energy and things like that. So lecture on Friday will be all about the partition function and what it is for atoms and molecules, and then how that partition function relates to internal energy, entropy, Gibbs free energy, and things like that, right? Basically, all thermodynamic quantities we've talked about in this class can be directly computed from the partition function, okay? Even equilibrium constants, okay, rate constants, anything. I guess we haven't talked about rate constants, right? But equilibrium constants, free energies, all that wonderful stuff can be calculated from the distribution function, or the partition function, sorry, partition function. Okay. So again, any questions about kind of the Boltzmann distribution function, where it came from, what that functional form is meaning, anything like that? Yeah.
I was just wondering what chapter in the book this corresponds to.
This is, it's like chapter 15A or something. It's near the back of the book, right? So the book, the first section is like thermodynamics, then quantum mechanics, and then it's like, I forget what it calls itself, at the very last kind of, it's broken up into 3 sections, right? It's like, huh?
I think you called it kinetics.
Kinetic. Okay, so it's kinetics, yeah. So yeah, so this stuff is in that kinetics chapter, I believe, where you have a chapter or 2 on kinetics, and then there's a chapter on it's called like statistical thermodynamics is like the title of that chapter, and so yeah, so this is in that chapter. Yeah, I guess that's true. I don't have this in the syllabus, right? And so I don't have that chapter labeled, but it is in the book, and again, it's something like chapter 15. I don't know if that's exact chapter number, but around that area near the last couple of chapters or whatever in the book. So. Other questions? All right. So all right. So yeah, this is kind of a review of probabilities and statistics. Okay. I guess this question is actually one I'm more interested in next semester, but we'll talk about it. Whatever. Right. Anyone have a assumption as to like if I did this integral of some function of epsilon times the probability of epsilon, again, where p sub epsilon is the Boltzmann distribution, that probability function, what is this integral equal to? Is it equal to 0, 1, average value of E, average value of f of E, average value of PV, or something completely different? You want to take a guess? And value of E, close. So this is an average value type function, okay, type integral, right? So in general, in statistics, the average value of something is related with basically the sum, or in this case, an integral for a continuous quantity of that thing times its probability, okay? Right, I mean, again, when we think of taking average values of numbers, we just like sum up all the numbers and divide by the total, right, for that discrete quantity. Now, you could, and that gives you the average value, right? But you can also do that average value by saying, you know, if I had, right, let me share here, right? Right, if I had some numbers, 1, 3, 3, 5, I'll just do it like that, make it simple for myself, right? Say, okay, what is the average of that? It's, what was it? 6, 7, 12. The average value divided by 4 is 3, right? So the average value is 3, right? Average of this is 3, okay? Of that set of numbers, right? Well, I can get that average value as well by taking the sum of the number times the probability of being that number, okay? The probability of being number 1 is just 1/4, right? Probability of having number 3 is 1/2, right? The probability of being number 5 is 1/4 as well, right? It's the total number of being 1 divided by the total possible numbers, right? So 1 divided by 4, 2 divided by 4, which is 1/2, 1 divided by 4, right? So that's the probabilities, right? So I sum 1 times 1/4 plus 3 times 1/2 plus 5 times 1/4, okay? Right? And you do that sum, you will get 3, okay? That sum will come out to be 3, right? And that is, again, the average number, right? The average value of these numbers, okay? And then this can be generalized for integrals, right? The integral of some number times the probability of that number, right, is equal to the average value of that number, right? And so that's true in general, right? So this relationship here is the average value of f of E, right? It's the average value of this function is what this integral comes out to be, okay? Because it's that function times its probability, so that gives you the average value of that function. Okay? This is more important for next semester in quantum mechanics, where we'll be doing lots and lots and lots of these wonderful things, of taking average values and probabilities and things like that in quantum mechanics, because it's all kind of based off of probabilities and yada, 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 not so deterministic as Newtonian mechanics. Okay? So in the Boltzmann distributions I talked about, I assumed that each energy level has only one unique kind of state. There's only one unique state for that energy, right? You can have cases where there are multiple unique kind of states at the same energy, okay? And that is referred to as degeneracy, okay? So degeneracy is when you have 2 or more states that have the same energy, okay? Those states are referred to as being degenerate, okay? There's not some sort of negative term here in this case, right? I'm not trying to insult those states, calling them degenerates or something like that, right? It's referring to the fact that a state is degenerate, meaning it has multiple states at that same energy, okay? So in this example here, the lower energy state is considered doubly degenerate, and that first, the higher energy state is singly degenerate. It's not degenerate, right? That's how you describe it. Okay. How the Boltzmann distribution gets modified is you just got to multiply the exponential by g sub I, where g sub I is the degeneracy of that energy level. Okay, so if there's 3 states that all have the same energy, then it is g sub I is equal to 3. So right, so g sub I is just some whole number. It's 1, 2, 3, 4, 5, 6. Right, it's equal to the degeneracy of the energy. Okay, so again, in the example I gave, each energy level, there's only one unique state at that energy, so g sub I is equal to 1 for all values of I. Okay, but if there is some degeneracy of those energy levels, then you have to use this kind of general form where you include then that degeneracy. Okay. Any questions about that? Again, this topic, again, talking about degeneracy and such, is also much more related to stuff we'll talk about next semester in quantum mechanics. Okay. So talk about kind of some properties of this Boltzmann distribution function. Okay, so some of the things we can ask is, right, how do based off this Boltzmann distribution function, how would the energy levels change with the change in temperature, right, or the occupation of those levels, right, the probability of being at a given energy change with temperature. Okay. So let's first ask, right, what happens at very, very low temperature, right? Temperature approaching 0, do I expect all energies to be equally occupied? Do I expect all of the states to be at the lowest energy, everything to be at the highest energy, or no idea, need more information to figure out how these different energy levels will be occupied? You don't have any thoughts, right? As my temperature goes to 0, yeah, everything should go down to the lowest energy. Yeah, and that is true, right? You can work it out using the Boltzmann distribution function, right? And looking at the relative population of I level or the J level, okay? Right? You look at that, right? You have the relative kind of populations like this, right? As temperature goes to 0, right? I'm dividing by that temperature, so this term here goes towards infinity. So I have e to the minus like infinity times this delta epsilon, okay? And so the main question is delta epsilon greater than 0 or less than 0, right? Delta epsilon is greater than 0, then this thing goes to 0, right? But if it's less than 0, then this thing blows up to infinite, right? Infinitely large, right? And so what that's basically saying is any energy, right? And delta epsilon is, right, the difference between these two energies, right? So anytime you're increasing in energy as temperature goes to 0, the probability of that actually happening is going to 0, right? Which means that everything's wanting to go down to the lowest and lowest possible energy. Okay, and so yeah, so at temperature approaching 0, right, everything's occupying this lowest energy state, and nothing is in the higher energy levels. Okay, right. With what we're talking about with thermodynamics, right, we think of this plot being kind of like free energy, right? Okay, right. Where are my molecules spontaneously going to? It's related with their free energy. Okay, well, it's related with delta H minus T delta S. Well, as temperature is going to 0, delta H is what's dominating here. Right? And so it's all based off of what's at the lowest energy, right? It means I want to go to lower enthalpy, right? The lower total energy. So everything's going to want to go down to the lowest possible energy. Okay. While if my temperature is approaching infinity, what would we expect? A, B, C, or D? Yeah. High temperatures approaching, oh, it says very, yeah. Low temperatures approaching infinity, that makes sense. Yeah, states at very high temperatures, temperatures that are approaching infinity. So not quite. So what will happen here is actually A. They will become evenly occupied. Okay, you can look at, again, kind of the math of this, right? If you look at the math of this, okay, as the temperature goes to infinity, you now have e to the minus 0 times delta epsilon, which doesn't really matter. This is just e to the minus 0, which is just equal to 1. Okay, so the probability of I over probability of j equals 1, no matter what I and j are, right? Basically, they have equal probability, right? So as temperature goes to infinity, probability of being in all states, it becomes equal, okay, right? Right, and you know, again, like the very common thing to think of is thinking that they all go to the highest possible energy, right? Right, because as you get higher temperature, right, you have higher energy in your system. And it's not that, but the thing is even as you go to infinite energy, it doesn't mean that everything is at that highest possible energy. Okay, because you can still have some things at a lower energy and some at the higher energy and things like that, right? They're still going to be distributed across different energy levels, right? Things are not nice and organized. And again, you can think of that in terms of entropy. Okay. Again, thinking of this thermodynamically, delta G is equal to delta H minus T delta X, right? Well, right, at very high temperatures, right, delta H doesn't matter anymore, and all that matters is entropy, right? And entropy wants everything to be equally spread out, equally distributed, okay, right? The more things are spread out, the more random or chaotic stuff are, the higher the entropy, okay? And so you, right, at infinitely high temperatures, right, things want to just evenly spread out across these bins, right? Which again, statistically is what one should expect, right? If there's no constraint on energy, right, you're just asked what is the most probable occupation of these bins, right? For n particles, you'd say, well, I'd have the particles equally distributed across all bins, and that will have the highest probability, okay? And that's what you get out of the Boltzmann statistics, right? Is that, okay? And again, that is what entropy is really related with. It's just the fact that entropy is just a measure of statistics. It's a measure of probability of combinatorics, right? Of like what is most likely to occur just based off of chance, right? Based off of the fact that things, you know, are moving around randomly in space and things like that, right? It's most likely to observe an equal distribution of things than it is everything located in one spot, okay? That's all entropy is related with. So that's how kind of entropy again ties in with this talk of statistics and probability and things of that nature. Okay. So questions about these things, right? I think this next slide, right, has then kind of plot, right? What's being done here is, right, you're changing the value of beta times epsilon, okay? Beta being 1 over kt, so 3 going down to 0.3 means, right, you're increasing, say, the denominator, right? Epsilon, we imagine, is staying constant, and the denominator, kt, is getting larger and larger as you're going to higher and higher temperatures, right? And you see that things spread out to higher and higher energies, okay, as you get to higher and higher temperatures, right? But they're still actually more favored to the lower energy levels than the higher energy levels, even as you get to higher temperatures, right? So this distribution never is, right? If things are in a thermal kind of equilibrium distribution, okay, you should always have something that looks like this, where you have higher probabilities at lower energies and then lower probabilities at higher energies, even as you get to very, very high temperatures, okay? Now, the only thing that might modify this distribution a little bit is if there's some degeneracies going on at some of these different energies, but we're not going to consider that, right? Just talking about these being kind of singly degenerate, okay? And the only way you can get around this type of thing is if you have a non-equilibrium distribution, right? And to get that, you'd say, like, we'll talk about this again the next semester, right? If you were to say, hit something with a laser, right? Photo-excite stuff, right, from its lower energy states to higher energy states, right? You'd introduce a non-equilibrium distribution, and that could have much higher probabilities of particles at higher energy levels, a lower probability of particles at lower energy levels, but it's not going to be a stable distribution, and things, once they thermally equilibrate, get to equilibrium, right, relax back down, you will have a distribution that, again, looks something like this, okay? That satisfies kind of your Boltzmann distribution. Okay. So any questions about kind of these properties of the Boltzmann distribution functions, what it means, what it tells us, okay? All right. So given a two-level system with energy separation of 3 kT, so there's two energies, the lower energy, the higher energy, and the difference between those energies is 3 times kT. What is the relative population of the higher energy state compared to the lower energy state? So I got some A's here, right? And that is correct. It is A, okay? Right? That relative distribution of the two states, right, is given by this formula here, okay? Where this difference in energy is just 3 kT, and that's divided by kT, so it's just equals 3, okay? And so you're just looking at the Pi over Pj is just equal to e to the minus 3. Yeah. Which ends up being 0.0497. So questions about that? What assumptions are made when deriving the Boltzmann distribution? The energy levels need to be equally spaced. There is no interaction energy between the molecules. Temperature needs to be very high. All possibilities for the distribution of energy are equally probable. A, all required. B, all but one. All but I. All but, yeah, you can read. Anyone have any thoughts? F's, D's. All right. So the energy levels need to be equally spaced. That is not required. So right when we talked about at the beginning, I tried to mention right that was equal spacing. It's just an example, but there's nothing that requires the spacings to be equal. Okay? So they do not need to be equally spaced. But we do assume there's no interaction energy between the molecules. Okay, there's no assumption being made about temperatures. Okay, but then we do assume that each weight each configuration, each way of distributing your particles is equally probable. Right, that there's nothing favoring one distribution over another besides just the number of ways that you can create that distribution. Right. So yeah, so F here, 2 and 4 are the only assumptions that are being made for the Boltzmann distribution. Okay? So the question here, right? And so this type of question, right, is one that you could potentially see appear like if something related with this stuff is appearing on exam, would be kind of a question like this. Okay, so just giving you an idea, right? That like here, I have say this energy level diagram for just two states. Okay, and the question is at what temperature will the probability of occupying the second energy level be 0.15? Take a little bit of time here, work on this self. All right. So, right, in this problem, we're given a two-level system. We're asked what is the probability of being in the higher, or what temperature will the probability be at a higher energy level of 0.15, right? So what is that temperature equal to? Okay. Right. The formula for that probability of being at, say, energy level 1, right, is just e to the minus epsilon 1 over kt divided by q, right, which q is just the sum of up over all the possible energies. So it's e to the minus epsilon 0 over kt plus e to the minus epsilon 1 over kt. Okay. All right. So any questions about where I got this formula? Right, so this is the Boltzmann distribution formula, right? Again, in any any type of problem, whenever we're trying to consider what is the population of at a given energy, right? The type of distribution, right? The type of probability function that describes that is the Boltzmann probability function, right? So the Boltzmann distribution function describes the probability of being in these different energy levels, okay? And so just plugging in for these things, right? I have this P1 equals E to the minus, I'm going to leave it as epsilon 1 divided by KT for now, okay? Epsilon 0 is just equal to 0 by definition, right? So this is 1 plus E minus epsilon 1 divided by KT, okay? Right? And so, so now we have this equation that I can then use to solve for temperature, okay? So this equals 0.15, right? We're asked what is the temperature such that that equals 0.15. So I can multiply this over, right, and get 1 or 0.15 plus 0.15 e to the minus epsilon 1 divided by KT equals e to the minus epsilon 1 divided by KT. Okay. Right? I then subtract this over here, okay, and get 0.15, okay, it's going to equal e to the minus epsilon 1 divided by KT, where I have 1 minus 0.15 is the number out in front here. It's what, 0.85, okay? And I'm just going to divide that onto the other side, so I'm going to do 0.85 over here, okay? So what I did, oh, sorry, that's kind of going off the screen, right? So what I did, right, is when I subtract this over, I get 1 minus 0.15, which is 0.85, and then I divided 0.85 onto the other side to just get this relationship here. Okay. And then we can just take the natural log of both sides, right? So the natural log of 0.15 divided by 0.85 equals minus. Now I'll plug in for epsilon finally. Epsilon 1 is, it's not on the screen, right? But this is epsilon 1, right? Epsilon 1 equals 0.0372 electron volts, okay? It's plugging in for what K is and epsilon 1, okay? So this is minus 0.0372 divided by 8.617 times 10 to the minus 5 times temperature, okay? Both these things are in units of electron volts, so the units cancel. We don't need to worry about it. Well, K is electron volts per Kelvin, and so your final answer will be in Kelvin, okay? Right? And so that is everything we need, and we just got to plug in the numbers, right, to solve for temperature. Okay? And I'll flip back to the slides to show what the final temperature comes out to be. Okay? But any questions about this? About how we went about solving this problem, right? And the idea of this problem is we're identifying the fact that we have some discrete energy levels. We're curious about what is the ratio of occupations, right? The probabilities of being those energy levels. That probability is always going to be given by this Boltzmann distribution function. So we just got to use the Boltzmann distribution function to kind of solve the problem, because that problem relates to the temperature and with the probabilities of being those energy levels and their energies, right? So any questions about how I went about solving this? So let's flip back to the slides here. All right, so and kind of going through plugging all that stuff in. You get final temperature is 248.8 Kelvin. Okay. So once you plug in for everything, that is the final temperature you will get. And so at that temperature, the probability of being in that first excited state is 0.15, right? 15% probability of being in that first excited state, right? 85% being in the ground state. Okay. right? Again, if you were to look at this two-level system and consider, a temperature at, 12,000 Kelvin, what you'll calculate when you do that, if you consider this two-level system at a temperature of 12,000 Kelvin, you'll calculate the probability of energy level 1 and probability of energy level 2, both being basically 0.5. Okay. Right. And so, yeah, right. What you'll find is, again, equal occupation of those two energy levels as the temperature gets larger and larger and larger, right? And again, you're never going to find a case where the occupation is, say, inverted between the excited and lower energy state. Because again, Boltzmann distribution is assuming a equilibrated system, things that's thermally relaxed, right? We're at equilibrium and such, okay? And in those cases, you always have this kind of lower energy states have a higher probability than higher energy states, right? You only kind of invert that when you're in non-equilibrium states, non-equilibrium systems. So questions about the Boltzmann distribution function, what it's related to, what it means, how we got it, how we use it. Again, this type of problem is kind of the most relevant to what will potentially be on for this class. But all of this is very important and very relevant to next semester when we talk about quantum mechanics, right? Because we'll use this Boltzmann distribution, things like that, to kind of use some of the things we discuss and solve for in quantum mechanics to then relate those things to real life observations and relate these things with spectroscopy. So this Boltzmann distribution plays a role in spectroscopy as well, plays a role in sort of the peak heights and things like that you get in spectra can be related to these Boltzmann distribution functions for certain types of spectra and things of that nature, right? So this pops up a lot of different places, a lot of different times in different aspects of physical chemistry. Okay? So it is very important and very relevant. Okay. Any questions at all? So if there are no other questions, we'll just kind of end it here today. Again, on Friday, we'll talk about the partition function and how that partition function relates to our thermodynamic quantities. That will be the last kind of lecture of new material is this Friday, right? And then afterwards, we're just reviewing and doing exams and such for the rest of the semester. What fun, right? Again, for those who are here in the class, I have your homeworks and you can pick them up. For those on Zoom, if there are no further questions, and I'll close out the meeting, but I'll wait just a minute just in case someone has any questions they'd like to type up or ask. Okay.
So for that question, if it's a two-component system, right? Or
Two-level system, yeah. Two-level.
we can figure out just PJ from the beginning and then just use that same equation we did before. PI is 0.15, PJ is 0.85.
And since it's two level, you know the probability.
Yeah. So yeah, you could use the ratio. Yeah. So the question is do you have to kind of use just the thing for PI, or can you use the ratio equation PI divided by PJ, right? And yeah, in this two-level system, you can, since there's only two levels, you know the probability of the second level based off the probability of the first, right? Or vice versa, right? But you know the sum of those probabilities has to equal 100% or 1, right? And so, yeah, so you can just use the ratio of probabilities and not necessarily plug in for Q if you want to. That's for sure something you could do. Yep. So. All right. Because actually, if you saw, that's what I ended up getting, right? I ended up getting right here, right? I had e to the minus like delta epsilon, which is just epsilon 1 minus 0 over kt equals 0.15 divided by 0.85, which is those ratio of probabilities, okay? So yeah. All right. Doesn't look like there are any questions from those on Zoom. So I'll close out the session and see you guys on Friday.